Okay, so this is Aaron Murakami with A&P Electronic Media at emediapress.com, and today is March 7th, 2020, and it's noon Pacific time, and it's an honor and a privilege to have Jim Murray live on the call with us today, and we're going to be covering some, just going over some basic announcements, and then once we get started and we open up for questions, if you're muted out, all you have to do is hit 5 star, and that'll put a little flag up next to your phone number, and I'll unmute you, and I'll just say what the last 4 digits of your phone number are. Then you can just introduce yourself and ask your question. We'll probably go for about an hour, and as long as there's enough questions and Jim's open for it, we can go as long as he'd like. And so we have our upcoming Energy Science and Technology Conference. It'll be the 9th annual event that we've had in Hayden, Idaho, and this will be on July 8th through the 12th, which is a Wednesday through Sunday, and that'll be in Hayden, Idaho, which is about an hour drive from the Spokane International Airport. We have 18 different presenters scheduled who will deliver 20 different presentations. There'll also be 3 panel discussions and 3 workshops, and there'll probably be 7, 8, maybe even 9 different demonstrations, which is a record that we've ever had at one single conference to have that many demonstrations. And 1/3 of the seats are already sold out. A quarter of them sold out within 24 hours of me announcing that we're taking tickets or accepting payment for tickets. And so if you want to get your tickets for the Energy Science Technology Conference, you can go to EnergyScienceConference.com. You can see the schedule, the speaker bio page, the registration page, and once you register, and you finish registration, that'll take you right to the PayPal payment page. Also, one other site is vril.io, that's vril.io, and that's the page where we have some physical products, such as the Bedini RPX sideband generator, which is like a Rife frequency type device, and also an authentic electrically correct reproduction of the Lakhovsky multi-wave oscillator. And one other website is emediapress.com, and that's where we have all of the presentations from the conference available as digital paid downloads, and also any of the books or PDFs. Some of Jim's presentations include, I believe this was maybe at the 2012 conference, the first one, is called Tesla's Hidden Discoveries, which is at teslashidden-discoveries.com. A few of Jim's other presentations include Dynaflux Alternator. There's various names, but at Dynafluxalternator.com, there's a package of various different video presentations and PDFs and PowerPoints relating to his Dynaflux alternator. There's like a lab tour, a patent collection. Another one is Fundamentals of the Transforming Generator, which is at emediapress.com/Jim Murray/TGen. There's also another presentation on Jim's SERPS technology, Switched Energy Resonant Power Supply. I believe that's what it stands for. And that was a co-presentation several years back that he did with Paul Babcock, and that's at teslaspowermagnification.com. And then the most recent presentation from year before last is The Meaning of Unity and Energy Conversion Systems. And if you're interested in verifying the input versus output on various systems, that's at emediapress.com/Jim Murray/Unity. And just within the last, I don't know, maybe 4 to 6 weeks ago or so, we finally have Jim Murray's new book available on Amazon. If you go to Amazon and you search for Meaning of Unity in Energy Conversion Systems, you'll see Jim Murray's new book there. And let's see, before we open up for questions, is there anything in general that you want to cover, Jim, or do you want to maybe give a synopsis of what each of the presentations,
we can backtrack and cover the essentials of previous presentations. I don't have a problem with that.
Okay.
And then we can lead into a whole series of questions instead of just focusing on the book,
Sure. Okay, you want to start with kind of a basic overview of your first presentation, which was Tesla's Hidden Discoveries?
Well, basically what I tried to do in that particular presentation was to recap in a modest way the entire series of events that led up to some of my earlier discoveries and some of the unusual individuals that helped me along the way, either by educating me or by just stimulating my imagination. I would say that looking back on that, you have first and foremost, of course, is Nikola Tesla. And then after that, you have some unusual individuals like Gene Carini and Otis T. Carr and Warren Getz. And after that, the list is nearly endless of all the characters I've intermixed with. But the bottom line is that my association with people of that sort not only changed my thinking, but it broadened my scope of appreciation for the way the world really works. Because when I was first starting out as a physics student, I was mostly interested in particle accelerators. And, when I get into something, I try to get into it very deeply. So I was hyper-focused on just that subject and things related to it, like high vacuum technology and ion sources and power supplies of different sorts. And sometimes it's like having blinders on when you're so passionate about a particular subject. You don't always see what's going on around you. And when I was a senior in high school, I was really, really focusing on making it into MIT. And I wanted to study particle physics and related subject matter. And then my dad died in my senior year, and without his help, I could never have afforded MIT, and I wasn't smart enough to get a scholarship of any sort. So I went to work in the shipyards in New Jersey and just squirreled away my money until I could afford to go back to college. And my life took a really different course as a result of all those things. Mm-hmm. But I have no regrets. I mean, I think I really had an interesting life, and I'm still hopeful that some real good can come of the things I've learned. So, you want me to jump ahead into one of the other subjects, or do you want me to sort of highlight the things that I tried to feature in the original presentation?
Let's see. I think maybe we can go on to some of the other presentations. I think it'd be good for some of the people who called in to, hear directly from you a synopsis of each of these technologies. So I guess the next one would be going to talk a little bit about the Dynaflux Alternator.
Yeah, that was well, it still is a very special technology from my point of view because of the way it was, the way I found it, let's put it that way. I was working in northern Michigan in a little mining community on Drummond Island, and I was doubling not only as an electrical foreman, but I also did a lot of consulting work for the local power company. And it was in the early years of my association with Bethlehem Steel that I wound up meeting somebody that was really quite a mentor and a dear friend to me, and that was Guy Obolensky. And we talked about so many different things together, and that was a real eye-opener the man was doing some extraordinary things, and he more or less prompted me to just follow my own intuition and do things as I saw fit to do them, rather than worry about sticking to the books. So in that respect, I owe him a lot, because I've been doing that ever since. But more particularly, he encouraged me to make use of the information I already had and see if I couldn't come up with something that would benefit Bethlehem Steel, so that they would more or less be excited about the capabilities. And at the time, they were scrapping out a 1928 Bucyrus Erie electric shovel. And I went to the management people, and I really begged them to let me take the guts out of the machine, and they could scrap the superstructure. And they wouldn't have made that much money on the extra parts, so they said, yeah, go ahead, take it. What are you going to do with it? So I said, well, in my spare time, I'll build you a device that I believe will save you a considerable amount of money on your monthly bill. And, of course, that turned them on. And it took me about 3 years in my spare time, but I built a pretty good-sized synchronous capacitor. And then we put it online, and it operated flawlessly, from the beginning, which even surprised me. But the cool thing about it was that it knocked their demand way down. I believe we saved about 20% on their power bill for a couple of years that was in operation. And so they were very pleased with it, and they said, well, if you want to use it to do experiments and things like that, we'll help you. And the more you learn about it, maybe the more money we'll save. So I instrumented the thing at their expense and began doing a lot of different experiments, especially on the third shift, because there weren't too many people around. And I got a real brainstorm one time working with the local operator for the regional power plant in Detour, and I wanted to try an experiment that was a little bit risky. And so basically we waited until there was a power outage between Sault Ste. Marie's generating station and Detour, Michigan / Drummond Island communities, and they started up their standby engines. And they were I forget the name of them, but anyway, they were two 5,000 kilowatt machines. They were big enough to support the local community as well as the line over on Drummond. And with the power outage between the Sioux Locks and Detour, there was a very close match between the amount of power that they were generating and the VAR capacity of the machine that I had put together. And so I had artificially changed the reference from 60 cycles to a variable frequency input. And what I wanted to do was to slowly bring up the frequency until it was at a 2-to-1 ratio and see what that would do. Of course, it was a little bit of a daring experiment because people's personal equipment was attached to the line, but my curiosity really propelled me forward regardless of the risks. And so it turns out that the night we did this, it was a terrible ice storm, and it was really coming down. It was very, very cold, and it was around 11 at night, I think, when we finally fired this thing up. And I was in telephone communication with the gentleman at the generating station, and I told him to keep me appraised of what was happening, and I made the adjustments on my machinery and brought up the frequency And as we started to get further and further away from 60 cycles, all hell broke loose around the community. I mean, Christmas decorations were exploding and people's personal things were behaving strangely. But anyway, I persisted, and when we got to 120 cycles, all of a sudden, all the power that was being delivered intensified, and the load went off the two diesel engines, and the operator couldn't understand that. And frankly, I couldn't understand it either. I mean, this was not something I anticipated. And so luckily I had recordings going of the basic parameters involved in the experiment, because it didn't last that long. I stepped out of the building that I had my equipment in and looked up at the transmission lines, and they were glowing cherry red despite the low temperature and the freezing rain. And just seconds after that, a huge fireball erupted out of the cable crossing on the St. Mary's River, and the entire system went down. But it was the analysis of those recordings and a lot of deep thinking that basically stimulated me into trying to do the experiment on a miniature basis. And those efforts eventually resulted in the discovery of the Dynaflux principle, which I then proceeded to get a patent on. And that was, the original work was in the late 70s, and I think the patent was issued in 88. So it took quite a few years to get it through Washington. They rejected it many different times. And luckily I was single then, because every penny I made went into that procedure. And I eventually got the patent, but nobody ever funded it. So aside from educating me, it didn't do any good, as far as helping the world is concerned. But I'm still investigating that machine. It's much more complicated than you can ever imagine.
And is that the actual genesis to SERPS? Because some of the principles involved sounds similar about the load canceling and so forth.
Yeah, well, what happened there is really kind of interesting. It cost so much money to do each prototype, and as I geared things up to larger and larger power levels, the expenses went up exponentially. And so eventually I reached the point where I started wondering, if this is a universal principle and it's really applicable across the board, I should be able to find a parallel to it in an electronic application, and maybe it would be applicable to something other than direct power generation. And that line of thought eventually brought me to consider the possibility of building an electronic device which would be on the receiving end and would actually cause the electric power delivered to the customer to behave in a manner similar to what was observed in the Dynaflux Alternator. And in the years that I first started tinkering with that idea, I was basically brought up as a tube guy, and I didn't have the time, considering all of my other activities, to keep up with the development of solid-state stuff. But the first couple of devices that I built along the line of SERPS were all done with great big power tubes. They were triodes that I had gotten on Radio Row in New York years ago, and I used them to tinker around with the basic concepts. The biggest problem is that unless you're dealing with some really large industrial tubes like igniotrons, for instance, you're just not going to have the amount of amperage involved that'll do a household any good. But I persisted anyway, just looking for something that would lend credibility to my own theory about the thing. And eventually I met a guy who was a Navy SEAL, or he was actually an ex-Navy SEAL, and he had done a lot of really unusual work in power electronics for the Navy, and he was kind enough to introduce me to some of the more recent switching devices that had developed since my initial interest in that direction. And together we built 3 or 4 other prototypes. And then he wound up going back in the Navy or something. And I had to quit for a while. And then I met a Chinese fella out in New Jersey who had an electronics company, and his mode of operation was to build custom circuitry for people, and then after they were perfected, go into mass production for them. So I thought that would be an interesting thing to do. And so he built me actually one of the first most successful SERPS circuits. And the biggest problem I had at that point was making intelligent measurements. And I was married by then and had a little girl. And so my wife almost left me when I wound up taking a second mortgage out on the house just to pay for the instruments that I bought. And I bought about $60,000 worth of equipment just to test the original SERPS device. And if I hadn't made that investment, I would never learn the things that I did. So ultimately, I realized that the best way to make use of the SERPS circuit would be to combine it with an alternator as a self-contained pair. And that led me into some of the other embodiments that I later covered in the SERPS patents that I applied for. And I'm still working on that stuff too. It's not as simple as it sounds. That's all I can say at the moment.
Mm-hmm. Now, on the other presentation on the fundamentals of the transforming generator, from what I recall, this is something that Guy Obolinski was also he was experimenting with one of your original prototypes or something, and wound up speeding up and self-destructing or something like that. It's kind of like something out of the movies where you short it out and it starts to take off into runaway mode, where it just gets faster and faster and you literally have to turn it off before it does self-destruct. I think that was a presentation you gave at, well, it was either at the Hayden Eagles Lodge or the downtown Coeur d'Alene one. But I think one of the applications I know that I'm interested in is that it seems like, for every 100 watts you're putting into it for lighting applications, that you're actually getting quite a bit more in light, for example, lighting up fluorescent tubes. And it sounded like it might be, because the Dynaflux seems to be pretty complicated, and the average experimenter would not even be able to do that unless they're willing to, put a lot of money into it. But it sounded like the transforming generator might be able to be replicated at some level by simply rewinding some off-the-shelf motors. Maybe go into.
Oh yeah, that's how I did it. I mean, I didn't have money to pay for the machine to be designed for me from scratch. Basically, what I did was I got a hold of some old wound rotor motors, and I paid junk price for them. And then instead of using them as a motor, I used them as a generator. But I had to strip the stator windings off in order to do that, and then I rewound them myself in the format that I was interested in pursuing. And the darn thing worked beautifully. and what it was capable of doing. And I think this is the reason why Obolensky was so enthralled with the machine, was the fact that if you connected it a certain way, it could automatically supply conjugate impedance to whatever device it was powering. And I discovered this when I was still in Michigan. I used, I think it was either a metal halogen lamp or a mercury vapor lamp. I think it was a mercury vapor lamp the first time. And I found that I could connect it up to this generator without a ballast. And it just lit up beautifully. And the amount of lumens that were coming out of the thing were well in excess of what you would normally see, from the same lamp lit traditionally. And I told this to Obolensky. I said, I think the damn thing is so bright, that it's got to be doing something different. So I used to have off in the winter months because in northern Michigan, the temperature goes down really, really low. It's like 50 or 60 below zero, and we get 200 inches of snow a year. So the mine basically shut down, and I had like 3 months off with pay, which is a pretty unusual situation. So once they shut down on that particular year, right after they shut down, I loaded all my equipment in the back seat of my car and drove all the way down to New Jersey and then up into New York State to visit with Obolensky. And we set the thing up in his shop. And he had all kinds of equipment that I never dreamt of. So, he was saying, yeah, you're putting out so much light here that this device is bordering on the same kind of performance that I have achieved with my, he had a device called a phaser ballast. And as a matter of fact, he was really concerned that I might become a competitor to him. And I said, look, that's not my intention at all. So we signed an agreement that I wouldn't muscle in on his territory and, that type of thing, just to keep our friendship intact, because I didn't want him to worry about something that would never happen. And I couldn't very well bring the thing to my mother's house where I was visiting at the time, so I left it at Guy Obolensky's lab. And while he had it in his possession, he did some rather unorthodox experiments. And he claimed that he never remembered what he did. And I know Guy Obolensky too well to believe that. And I took it as whatever he did, he didn't want to share with me. And I let it go at that. But basically what happened was he got the thing into a mode of operation where it took off like bat out of hell. And it spun so fast it threw the windings off the armature. And then I had to pull the thing all apart, cut away the extra windings and that had spewed out into the air gap. And then I had to redesign the power supply for the field excitation to operate at a slightly lower flux density. But I actually had the thing attempt to do that to me a couple of times many years later when the Japanese were funding me. And as a matter of fact, I learned how to encourage it. And so we had a demo film made that showed the thing in operation in Las Vegas in George's machine shop. He's my longtime buddy and mathematician who's helped me with all kinds of things over the years. And the only thing is the breakers there were pretty sensitive because he had a lot of CNC equipment in his shop at the time. And so it never reached really high speeds. It just tripped the breakers. But it did take off a couple of times on film. And I believe that demo is still floating around somewhere. But the reason that I personally was interested in the transforming generator was because it allowed me to study the difference between a spatial or emotional voltage and an actual voltage. And the difference is, of course, one is created by motion and flux, and the other voltage, the one that people are really more familiar with, is actually created by a current passing through an impedance. That's why you have IR, IX sub L, IX sub C, is because those voltages are current dependent. And yet they are always, well, not always, but they are most often assumed to be equal. And I would say under a large number of arrangements, they can be treated as equals without a problem. But there are some times when you really have to understand the difference if you want to make use of that difference. And so that's the reason why I pursued that. And then, of course, when I met Paul Babcock, he introduced me to a friend of his who really was quite a hotshot with motors. His name was Dave. I won't say his last name because he's no longer with us. But anyway, he got a hold of me after that and asked me if he could experiment with the concept and for the purposes of making a motor. And I said, sure, why not? I'm not working in that direction. I have no problem with that. So we signed some agreements together and clarified exactly what we were doing. And then he basically applied the same principles to a three-phase motor, and he wound up with a very small engine that had a footprint maybe a third of what the standard size frame would be for a motor of equal kW rating. And the thing just worked like a charm. And then unfortunately, he passed away, and Paul took over the R&D on that. And of course, he's had his ups and downs recently. So there's plenty to be learned from all this stuff. It's just that it's like everything else, you know. If you buck what's accepted as classical wisdom, it's very hard to get funding. And so, you know, these things reach a certain point in their development, and then they just seem to stagnate. But they don't go away completely. I always hoped that I could interest enough people that they would be interested in pursuing this, even if it's on their own. You know, we can always work out some deal. But I've been disappointed because even though I've been pretty open about a lot of the inventions that I've put out there, to my knowledge, very few people, if any, have bothered to even experiment with this stuff. So I think it's the same old story where the only person who really loves the invention to the point of passionately pursuing its development is the true inventor. Other people just say, oh, yeah, isn't that interesting? And they let it go at that. And that's been my experience anyway.
So a couple things you brought up about the transforming generator. So just real quick is when you're talking about the two different types of voltages, does it basically come down to one is voltage potential, like, for example, what you would measure at an open circuit battery just sitting there, and the other type of voltage is the electromotive force or the EMF. Would you say that's the two categories?
No. The one category is correct, and that is that emotional voltage, or I think it goes by some other term as well, but the basically it's defined by BLV, which is the flux density times the length of the conductor times the tangential velocity of the rotor. That is the kind of voltage that is referred to as a motional voltage or a space voltage, or I think it has some other more sophisticated names. The other one is the voltage that's created by the current. Now, if you take an ordinary resistor, for instance, and you put your multimeter across it, you'll read 0 volts. But if you pass a current through it, then you get IR. So that particular form of voltage is a potential drop, which is the product of the current involved and the resistance in that case. But it also holds true to some extent with, especially in AC circuitry, with inductors and capacitors as well. So the voltage developed across a capacitor which is in series, with something, and you have a current flowing through it, is I X sub L, where X sub L is a capacitive reactance of the device in question. The presence of the I in that circuit tells you that the V is equal to the product of I and X sub L. So it's a voltage that's current dependent, just like V equals IR is current dependent, or V equals IX sub L is current dependent. So those are the two different types of voltages that I was referring to.
Okay. And in layman, in the simplest terms you can, what does it mean when you say that the transforming generator supplied a conjugate impedance to the light, to the load?
Yeah, that's pretty simple to explain. So basically what conjugate means is that if you have a circuit with a capacitance in it and you want to maximize the flow of current at a particular frequency, you put a series inductance in the same circuit and tune it so that the inductive reactance is equal and opposite to the capacitive reactance. Then you have a conjugate cancellation of the impedances involved. Well, it turns out that you can play that game with the time-varying inductance associated with the transforming generator. So in a lamp like a mercury vapor lamp, for instance, you're essentially dealing with the capacitive type of load. And when you power it directly, without a ballast, directly from the transforming generator, because the coupling in the windings is directly proportional to the current draw of the device, if you have a lamp that's cycling at a particular rate, the current is changing, the current requirement is changing with a particular phase angle and amplitude and what have you, and the windings automatically change their coupling coefficients in such a way as to arrange the voltage and the impedance of the windings themselves in such a way that the best amount of power is transferred from the generator source to that load without the need for the ballast device. Actually, you can study up on this just by looking at the teachings associated with the maximum energy transform. The maximum energy transfer theorem, which works for AC and DC, but it's a little bit more complicated in the AC because you have to take conjugate compensation into effect. And I had at one time a physicist that was very interested in using that to excite plasmas. And we talked for a long time on the subject. And I encouraged him to try it because it sounded like a good idea. And he never did anything with it, but believe it or not, Obalansky did. And that got involved with his faster-than-light experiments and a whole bunch of other things he was doing at the time. And it was kind of difficult to work with him on anything because I was in Michigan and he was in New York. But I used to go and see him as often as I could. And you know how it is. You have to live your own life, so nothing ever came of that either. But the potential is still there.
So now on the SERPS, there's some older demonstration videos. I think I have some of them on my YouTube channel, as well as a transforming generator one where it like shorted out or something and then it just like speeds up. If anybody goes to youtube.com/Aaron Murakami, and then on my channel you search for Jim Murray's name, there'll be a handful of interviews and there's some videos that Jim was kind enough to provide for me where you can see some of these demonstrations. And there's an older demonstrations with the SERPS where I believe it's heating up some inductive resistors, and it looks like most of it is being almost all of it is being returned back to the source. And then when you and Paul gave the presentation at the Energy Science Technology Conference, I don't know, that was maybe around 2015, 2016, something like that, that there was 50 watts of bulbs being lit up, but only a net loss of about 1 watt from the power supply, which is about 5,000% over. And then with working with Paul here in Spokane, where he had an old Onan generator set up with that type of circuit, it had a certain amount of gasoline, and it would run the engine at idle for so long. And then with the circuit attached, the SERPS attached to it, lighting something like 1,500 watts of bulbs, it ran just as long as it did as if it was idle since it was unloaded. And so would it be accurate to say that, when 50 watts of bulbs are being lit, but only 1 watt is the net loss from the input, it doesn't mean 1 watt is lighting 50 watts of bulbs. It means 50 watts of bulbs is 50 watts is lighting 50 watts of bulbs. And then if you're able to capture that on the back end and run it back through there, and with a little bit of loss, say 1 watt, then maybe 49 watts is lighting 49 watts of light as it's returned. So the net loss is 1 watt. Would you say that's more accurate than saying 1 watt is lighting 50 watts of bulbs?
Yeah, as a matter of fact, there was a lot of negative publicity over that statement, however it evolved, because people really believed that I was trying to say that, the system itself was 50,000 times efficient or whatever they thought it meant. But there's a very, very interesting situation associated with that whole phenomenon. And it has to do with, it's kind of like a an understanding that's halfway between Dynaflux concept and the SERPS concept. And the reason why it evolved at all was because of the fact that the original SERPS device was completely solid state. There were no moving parts. And I could demonstrate any day of the week on the benchtop prototype that I could heat up a resistor, a good-sized power resistor, to about, I forget if it was 30 watts or 300 watts, but whatever it was a goodly amount of heat. And I had it instrumented with Yokogawa watt analyzers, and you could, check the wattage, and let's say, we'll call it 30 watts just to be on the safe side. We check it, it says 30 watts, move the control to VARs, and it was 0 VARs. So you know that it's exactly a power factor of unity, and there was no screwing around. But then if you moved the equipment to the supply side and looked at it with the same instruments, the thing reported something like 5 watts, which is a 600% gain. And people would look at that and say, oh, you can't do that. That's violation of the laws of thermodynamics and this and that and the other thing. Where in truth, it wasn't a violation of anything. If you switch to looking at VARs, you had a phenomenon there where it was like, I forget the numbers exactly, but let's say 250 VARs flowing in and out of a resistor. And so, that's an even worse thing to show somebody, because then they say, well, wait a minute, you can't have a resistor producing reactive power. And, if you're up against a standard engineer that's not interested in thinking outside the box, it's a hopeless argument. You can't go anywhere with it. Mm-hmm. But actually, it wasn't that way at all. It was the other way around. What I had rediscovered was something Tesla talked about, where the watts themselves were reactive. So what we're talking about is you basically borrow so much wattage from the line and you send it back to the line, and the metering only sees the difference between the two movements, but the load looks at the absolute value. So one calculation or one measurement approaches 0, while the other one approaches a higher positive number. And it has nothing to do with, it doesn't even have anything to do with free energy, to be honest with you. It's just a totally different way of making use of electrical physics. And I've had more trouble trying to explain that to people. I finally gave up. It doesn't make any difference what you say or even what you show them. Somehow I think that you either have to be gifted with a very flexible mind, or else if you're completely schooled to the point where you can't accept anything new, then you're never going to see it. But I've made use of it, and that's the important thing. And originally, I was interested in using it for electric ranges and hot water heaters and things of that nature. Mm-hmm. Until I looked into the legalities of it, and then I realized that I wasn't there yet. Because if you have a really low power factor on any appliance that you're using, and believe me, the power companies don't give a damn what you did it with or how you achieved it, they have the right to penalize you for having a low power factor. And the fact that you might be pulling hardly any wattage doesn't help you at all. because the bill that you get from those people will be higher than the bill that you would get to run the appliance directly. So I pulled back on that and decided to combine that with a form of alternator technology so that it became sort of a duplication of the experiment that I did on a much larger scale in northern Michigan. And you now have a generator running a SERPS device, which is running the appliance, and whatever you have to supply to the generator to make it turn is what you pay for. But the good thing about it is that completely isolates the system from the power company, and so if you're buying power from them at one rate and using it at a different rate, I don't see how they can say anything, at least not in the normal legal sense. They may not like it, though.
Now, before we open up for questions, you want to take a couple minutes and kind of explain just briefly what the new book that just came out on Amazon is about, the meaning of unity and energy conversion systems?
Well, this is it's kind of an experiment in its own right, Aaron, because one of the things that I have noticed is that if you're up against somebody like a PhD and you try to explain certain things to them, I don't want to make any generalized statements. All I can say is that because of their education and all of the effort that they put into getting that degree, they're very resistant to certain types of new ideas. Mm-hmm. And just telling them about it or even showing it to them doesn't seem to make the right kind of an impression. So I figured two things. First of all, I know for a fact there's lots and lots of people out there tinkering around with over-unity devices, or at least they're hoping that there'll be over-unity devices. And so rather than to take a lecturer's point of view on the whole subject and try to explain various things that I did, it doesn't help. Because in reality, it took me many, many years to learn some of this stuff. And you can't, even if you're willing to give it away, you can't share it with somebody that's not prepared to receive it. So rather than just do a lecture or something like that, I decided to try and write the thing up in such a way that it would be an interesting read and it might shed some light on a mechanism which I found to be extraordinarily helpful in my research. And that was my main objective. The secondary objective was to see if there'd be a lot of interest in that kind of a teaching document, so to speak. So I wrote the thing up in very simplistic English and put as little math in there as possible. But basically what it's describing is the fact that in the early history of motor development, before people were aware of all the losses that you had to consider in designing a motor, they just realized, oh, hey, look, we can wrap a coil together and put a magnet in there and apply a battery to it, and it'll produce a torque. And it was such a novelty that you had people that just went ahead and built them and used them for different things. And I kind of cover the history of that in the first couple of chapters there. But then when people got really serious about it, it was about the time that Weston developed his watt meters, which were all portable and were really amazing engineering feat for the time, because they're electrodynamic in nature, which means they're an arson valve movement calibrated in true RMS measurements. And, you know, for the day, it may have been analog, but it was the cat's meow. I mean, it was just the kind of thing that experimenters were looking for, because now they could say, hey, I got instrumentation. I can measure what's going in and what's coming out, and I get some idea of, you know, a way of quantifying the performance of this device. And so in the early days, since they weren't even aware of all the losses that were out there, they had this thing called the pursuit for unity, which was basically a simple calculation where they took the input power and the output power, and they subtracted the known losses from the input power, and then divided through to get the overall system efficiency and multiplied it by 100%. And they noticed that you always wound up with a number less than 1. So it could be really low if it was a pathetic device that they were testing, or it could be much higher. And so this became known as the unity factor. And the idea was that when you had no losses, or else all the losses accounted for, depending on how you want to look at it, that the power that was being put in would manifest exclusively in the power that was measured at the output. And if it was 100% efficient, you'd have a 1 when you divided the output by the input. But on the other hand, if you had something less efficient than 100% and you wanted to quantify that, you would subtract the number of losses that you knew about from the input power and then make your calculation, and you would see some other number. Well, when I got involved with Dynaflux and some of the stuff I worked on with Obolensky, I was doing segregated load analysis just the way it's described in the IEEE manuals, because I wanted to do it right. And if I was going to apply for patents, I'd have to back up everything that I presented. So I made sure to research the right way of doing all these tests. And I was startled at the fact that when you subtracted out all the losses and then, you know, did a standard calculation for system efficiency, you got a number greater than 1. And I couldn't find anything that even talked about that. So it took a long time for me to clear my head as to what that means. But then suddenly I realized, well, wait a minute, that's telling you that there's something here outside the ordinary, because a normal setup, once you account for everything, will never give you a number greater than 1. And then I realized that all these people are trying to achieve over unity, and they've never heard of unity. Or if they have, they don't know what it means or what it used to mean. They don't even use it now. So I thought it might be educational to just sit down and create a little booklet that touched on that subject and clarified how I used it and how it can be used to find out if you've got just an ordinary tinker's toy or if you have something unusual. At least you have a way of knowing if you're on the right track or not. And that was my intention, and that's why I wrote it, with your help, I might add.
Okay. Yeah, so anybody can go to Amazon.com and search for Jim Murray's name or the title of the book, The Meaning of Unity in energy conversion systems. And also, if you're interested in any of the video presentations from the conferences, you can use the coupon code JIM50, JIM50, all capitals, in the shopping cart, and that'll give you half off for any of the presentations. Is there anything else you want to add before we start taking questions?
Well, you know how it is, man. I can probably talk all day on these subjects.
Yeah.
I think it's probably more important to let people ask questions if they want to.
Sure.
Here for that purpose.
Okay. So yeah, if you're on the call, I see a couple people have their hands raised. If you do want to ask a question, hit 5*, and that'll put a little symbol up next to your phone number, so I can unmute you and you can ask your question. And I'd like to ask if you can, keep the questions relevant to the topics that Jim has covered, and kind of get to the point. So the first one, if your number ends in 8537, go ahead and state your name, where you're from, and go ahead and ask your question.
Hi guys, this is Dayon from Ontario, Canada. I just want to thank you guys for having this call. And for Jim, I just wanted to ask, I have a few questions. I don't know where this will go, but for your Dynaflux and SERPS, is it correct to say those are a combination of some unusual geometry within the stator and rotor in combination with some unique switching circuits and controllers?
Well, in the Dynaflux device, it's definitely a question of unique geometry. There's no question about that. That's what I got the patent on. And, that's sort of immediately obvious if you look the patent over. When it comes to the SERPS device, it's a question of not only having unique circuitry, but also having the knowledge of how to apply it to achieve certain types of switching. And I say certain types of switching. I should be more specific and say knowing the effect ahead of time of timing the switching to produce a particular effect. The patent is out there, but I have to be honest with you that since I'm considering other patents, there's a lot of things that I don't want to get into in great detail at this point because it would constitute a disclosure, which never goes well with the patent people. But basically what it has to do with is an electronic imitation of the Dynaflux principle. And I mean, that's about as coherent as I want to be at the moment.
Yeah, and because I definitely recognize the interesting kind of geometry of Dynaflux, and I was reading the patents this past week, and for the most part, I did find it like pleasantly revealing in terms of just the overall operation. But yeah, the switching concept, I guess, for good reason, you have you gotta keep in certain aspects. I guess more abstract, just for the any future applications and that sort of thing. But it seems to me also there seems to be a portion of it that has to do with I guess what they would call sorry, the term's slipping my mind, but variation of inductance mostly to generate as well. So as you know, like a changing current can induce a voltage, but also the changing inductance can induce the voltage as well. So I wonder if you can speak at all about that aspect of changing inductance with respect to time to aid the system in its performance.
Well, I'd be happy to make a comment. It's a general comment, but it does address that same issue. You know, that if you have an inductor sitting on a bench and you pass an AC current through it, you don't have any problem making a measurement across it and, you know, measuring the AC voltage that's produced and measuring the current through it and investigating the phase shift and, you know, the I squared R losses and all that kind of stuff. And it's a very different calculation because you're talking about a voltage that's proportional to the inductance times the rate of change of current. Well, the interesting thing is that if you want to do that calculation from the standpoint of a straight impedance, all you got to do is measure the voltage, express it as an RMS number, measure the current, and express that as an RMS number, and then divide one into the other, and you're going to get another number that represents the impedance. And that impedance, of course, is X sub L. It's not the inductance. You'd have to divide by 2 pi FL to get L. But when you do get L, it's going to be a fixed number. Now, if you go to a generator, you don't have that same issue at all. You have something very different, because in the generator, the primary mechanism which develops the voltage is IDL-dt, which is the DC excitation current times the rate of change of L with respect to time. And if you equate that to a particular voltage, like let's say, you know, Vmax sine omega t or something like that, and you go through all of the calculations, you're going to find out that the inductance is actually time varying in that particular instance. And it's, if you got a traditional sine wave as an output from the machine, it most probably means that your inductance is varying as a negative cosine function. So, believe it or not, the same inductance also behaves as the traditional inductance does when the machine is allowed to produce a current, because you're also going to have a certain amount of I X of L drop within the interior of the generator as soon as you pull a current out of the machine. Now, I don't want to get into all the details because we'll be here all night, but the interesting thing is there's no way that inductive measurement can be the same as you would experience if it was sitting there on the top of a desk or a lab bench and, as a discrete component. And Tesla made a big deal out of this in some of his lectures, where he talked about the importance of never using RMS values as a primary means of doing calculations, because you would always introduce error. And I've been working for a very long time to understand exactly how he did these things. But I can tell you one thing. The shortcuts that people have taken, primarily since Steinmetz's day, have worked their way into a standardization in electrical engineering, which is not a complete reflection of the truth. And I don't know if that was done deliberately or if that was done for the sake of convenience. But the one thing I can tell you is that it has stopped progressive thinking along the lines that were originally opened for investigation by Nikola Tesla. So I'm kind of going to leave you with that, and hopefully that will give you something to think about.
Yeah, it definitely does. And in like you said, that varying inductance is something that, like, on your experience, that's present in basically all motors and generators, or just certain types like your Dynaflux?
Let me put it to you this way. There's so many different types of motors out there nowadays. I wouldn't want to make a blanket statement to say that it's always that way in every single one of them. But in the ones that constitute a discrete stator and a rotor that are traditionally designed, it's definitely the case.
Okay. And so something I also wanted to ask, and I'll definitely, I mean, I was there at the conference for I believe it was 2015, for the Dynaflux presentation. And I'll definitely be getting the rest of the presentations here and your book, just to learn more aggregated load analysis. But I wanted to know if you could speak at all. It might be difficult to talk about, but just your process in terms of these inventions and these patents. Like, you have a general, I mean, it might be difficult to speak on, but what's your process of kind of going through this? Is it mostly experimentation? Is it in combination with some theoretical background knowledge? Like, what gives you the most progress towards these type of inventions?
Well, I started off as a physics major, and I really learned at a very early age what the importance of always knowing the dimensionality of what you're dealing with. So basically, aside from learning the standard definitions for things, which certainly are certified over the years to be correct, at least for the most part, the next thing that you have to do is to learn the dimensionalities involved, you know, so that you can just look at something and realize what it means in another, from another point of view. It's one thing to get the numbers correct when you do calculations, and it's another thing to be able to say, okay, I know for a fact that volts times amps gives me watts, because I know what a volt is and I know what an amp is. And once you understand the fine structure of those two parameters, then when you multiply them together, you see why it's equal to a watt. And you can be able to take that all the way down to, you know, its most fundamental level, where a watt is joules per second, and a volt is a joule per coulomb, and an ampere is a coulomb per second. So, you know, all of these things are real important to learn, because when you're studying this stuff, whether you're on the theoretical side or even if you're trying to analyze something that's actually already been done, but you don't understand why it works, there's nothing more powerful to have in your possession than the really, really tight knowledge of the dimensions that you're working with.
Mm-hmm.
So,
in
to answer your question,
yeah.
It's not only the theory, and the ability to calculate, but it's also the dimensions involved. And I might add, too, that trigonometry and calculus are extremely important. And I have my limitations when it comes to calculus, but thankfully I have my longtime friend and partner, George, who is an incredible mathematician, and he's helped me in ways that I can't even begin to express.
Yeah, and my background is in physics too, so it's definitely inspiring to hear your story. And it seems also like you have some sort of, I don't know exactly how to describe it, maybe some sort of like spatial intuition, just to come up with these different geometrical configurations that, you know, that are not standard. So I don't know how exactly one might develop that, but maybe some of the theoretical background would help.
Well, it's very hard to explain the nature of inspiration. I mean, I don't even know how it works. I just make use of it. So,
yeah.
you know, that's the best answer I can give you.
Yeah. Well, it was good talking to you, and thank you for taking my questions. I hope to stay in contact with both you and Aaron in the future here, and I just want to thank Aaron also for having these calls regularly. They're very helpful and just kind of keep us all inspired and motivated to do more. So thank you guys, and I'll let someone else ask a question for now.
Thanks, Dan. Yeah, and I do want to mention that although Jim is not going to be presenting at this year's conference, he is. You are going to be there for the full 5 days.
Yeah, I'm planning on being there. So,
yeah. So if you want to meet Jim and you come to the conference, he'll be there pretty much all week. Let's see. Okay, if your number ends in 9598. I'm going to go ahead and unmute you. If you can say your name, where you're from, and go ahead and ask your question.
Hello?
Yes, go ahead.
Hey, how's it going? So I do a lot of computer-aided design.
What's your name? Hold on a second. What's your name and where are you from?
My name's Zach. I'm from Salt Lake.
Okay.
So I've recently come across you guys because I've been doing similar things, but in like a mechanical sense. I don't know, Jim, are you there right now?
Yeah, I'm listening. Go ahead.
How you doing? Yeah, so you talk a lot about a person in your life named Karini.
That's correct.
I kind of have a similar person in my life, but it's kind of a secondhand thing, and I've been trying to do something for probably 3 years or so, and I finally kind of understood what he's doing, which is why I started kind of trying to listen to. I came across what you guys were doing, you and like Paul Babcock and people like that, and it's essentially the same thing, but it's in a mechanical sense.
Sure.
So I was just wondering, yeah, like so when I started to first look at your designs, I noticed that have you ever seen Walter Russell, Tesla's?
Oh, sure. I know him well. I don't know him personally. But,
well, no.
Karini introduced me to his work, and I'm very familiar with it. And there's a rumor going around that he and Tesla collaborated on a couple of things. So, yeah, I know who he is.
Yeah, he has like a really similar design to your Dynaflux Alternator, except his is more like a bladed sphere, because your rotor is elliptical, but you could, the way that he did it, or at least he showed in his drawings from what I've seen, is it's more of like a three-dimensional ellipse, but it's pretty much the same thing. Have you ever seen that before?
No, actually, I have not. I would like to.
Oh.
So if you want to share it, get a hold of Aaron, and we'll
yeah,
some kind of exchange.
Yeah, I mean, like you've said in the past, like I've listened to a lot of your interviews ever since I kind of figured out that you were along the same lines as these other people. But anyways, I've been following this other person that's been it's not really along the electrical field, but it's along the mechanical, more mechanical stuff. But he's essentially trying to create an inertial propulsion system. And
okay, yeah, I'm familiar with those as well. Go ahead.
yeah, and when I saw your design, I was surprised that when you first started doing your Dynaflux alternator, that you I don't know, it's just I think that there's something to that, because when you start to alternate the rotor, and because the forces start to align with the rotor, rather than in like a typical generator where it's pushing back on the rotation, because it's aligned with the shaft. So this guy is trying to do something that's essentially the same thing, but he's canceling out, because in your rotor how it's basically 90-degree acceleration and deceleration cycles, right?
Yeah, go ahead.
Yeah. So he essentially is trying to cancel out the third and the fourth 90-degree cycle, so that you only have one acceleration and one deceleration. And from what I've heard, I mean, he's kind of like your Carini type person, like where I don't know. To me, it's kind of like a secondhand thing. Like I can't verify anything, but I've heard from other people that this is the case, and I guess I was just wondering, like, do you think that if you could, and I'm a computer-aided, I do computer-aided design, I do computer programming, and I basically do 3D models on the computer. So if you ever need any mechanical drawings or anything like that, I'll do them for free for you. But
well, I'd like to talk more about that because there's certain types of simulations that we have tried to do that seem to be impossible with standard software, simply because they're weird and they don't seem to comply. So get some kind of contact information from Aaron so that we can talk on the phone together in private, if you will.
Yeah, I don't really want to like say any names, but I've been looking into this for a couple of years now, and if you could, I'm trying to figure out how to say this, but it's really weird because I just got your videos and things like that like yesterday, and I got the email for the call today, and it's kind of strange in that way, but I don't know. A lot of these things are exactly along the lines that of other things that I've been looking into that have to do with propulsion rather than electrical generation, but the concepts are the exact same. And in terms of the way that it works, it rather than like the back EMF, because the back EMF is essentially inertia in an electrical sense, rather than, for example, a mass trying to accelerate or decelerate. But the concepts are the exact same. And if you can cancel out those two bottom quadrants in terms of your Dynaflux alternator, then you can basically make a system in terms of what this other guy is doing that I talked to you about, that was kind of like the Karuni in your life. and it will essentially make it so that I don't know, when you first started saying that you made the Dynaflux, you said that one of the things that you noticed is the shaft was oscillating, and that's because of the back EMF, right?
Well, the forces associated with it, yeah.
Yeah. So, I mean, there are ways of making it so that the shaft only wants to oscillate in one direction.
Yeah, I'm familiar
have you considered,
with the idea.
do you see what I'm saying?
As a matter of fact, the very first person that stimulated me in that regard was a guy by the name of Douglas Dean, and he had an inertial drive system that was presented in popular mechanics way the hell back in the 1950s.
Really?
And,
Wait, what was his name again?
Since that time, pardon me?
What was his name? I'm like really interested.
Douglas
Dean. Douglas Dean.
Dean.
Wait, he's not the Dean drive guy, is he?
Yeah, that's the guy.
Okay. Because I've looked into the Dean drives, and it's much different. It's a little bit different, but.
Oh
okay.
no, it's very different. But the point is, the idea that he was trying to achieve is pretty much the same. And I have known at least 6 people since that time that have been messing also with inertial drive systems. And I have an interest in it myself, but there's only so much you can do in a lifetime with them.
Yeah, I know.
So, I started into this stuff when I was 19, and today I'm 72. So I don't know where it went. Let's put it that way.
Yeah. Well, I've been, ever since I saw your stuff, I've been, because I do the computer stuff, and it's relatively easy for me, I've been trying to make your drive, or look at it in a 3D sense, and I know that you make your rotor by essentially taking a cylinder and taking a side view and then taking 2 cuts through it that create the ellipse. And then, but have you ever considered, I guess maybe I'm not that familiar with the math associated with it, but have you ever considered after those 2 cuts taking a top view of that same rotor that has now been made into an ellipse, and then making another cut so that it only has a deceleration component or only has a acceleration component associated with it?
Because no, I haven't done that because the things that I'm trying to achieve require symmetry from an electrical point of view.
Yeah.
But yeah, we can discuss that in more detail in a personal phone call, if you will, or if you want to.
Yeah, I'd appreciate that. I mean, like, if I'm not sure exactly if you how willing you are to do that, but I'd be willing to do that.
Zach, so Jim's offered that a couple times, so why don't you just email me and I'll forward your contact information to Jim. And that'll probably be the simplest solution.
Okay. Do you have an email address that I can contact you at? I'm sorry, this is I got an email from you, so that this is the only way that I know to contact people.
Yeah, just reply to any of the emails that I sent out, and it'll come straight to me.
Okay, thanks. I guess, can I do one more question before I leave? Or
yeah.
Should I leave it?
Go for it.
Okay. Just in one of your original videos that I watched, you were talking about, it seems pretty common that you keep talking about this example that Tesla made about the moon and the Earth. And one of the Yeah, one of the examples he gave was, or at least one of the machines that he made was based on that idea, and it was essentially just two gears that were the same diameter, and one was, it was pretty much like a planetary gear setup, and and I was wondering because you said that the sun gear, the central gear, was held stationary. And when I first heard about that that example, I figured that you were going to try to make some type of example where you attach the motor to the outer gear and then left both of the gears so that they could rotate, so that there was some type of inertial thing going on there. Because if the central sun gear had a ton of weight attached to it, then as you made that motor spin, if you attached the motor to the outer gear and it was basically acting as a pinion gear, then the inertia of the central gear would, prevent it from moving in some sense. But then you said that the sun gear was actually locked in place, and so I guess I'm wondering where the anomaly happened. Did it happen when did you try to spin it from the center point, like the lever that the outer gear was attached to, or did you try to, or was did something happen when you attached your motor to the, I guess what I'm saying is the outer gear, like the pinion, and then try to spin it?
Well, I don't want to get into that in great detail on the phone because there's a lot of proprietary stuff associated with that, but let me answer the question for you in a way that hopefully will satisfy your need to know. If you really want to understand what that technology is all about, you have to realize that the two gears that were free to rotate around the fixed sun gear, one of them was being propelled by a flexible shaft that goes back to an independent motor, which is in alignment with the central axis of the entire assembly. And the math associated with that is a lot hairier than most people think. And if you really understand it, it does lead you somewhere. And that's pretty much all I'm going to say about that on the phone.
All right, thanks, Jim. I'll get your information from, and I'll get
yeah, please do. I look forward to talking to you, Zach.
All right, thanks.
Okay, thanks, Zach. Okay, let's see, if your number ends in 3582, I'm going to unmute you. Go ahead and say your name, where you're from, and if you can get directly straight to the point if you have a question. Go ahead, you're unmuted. Yeah, if your number ends in 3582, you're unmuted. If you can introduce yourself and go ahead and ask your question.
Okay,
hello.
My name is Mike Shuckle. Hello, can you hear me?
Yes.
Oh, Mike.
How are you? I just wanted to put a hand up and say hi, Jim, and keep up the good work, my friend.
Oh, I'm intended to keep on going until I drop. How you been, Mike?
Mike has been very good, and I heard about the call, and I thought, hey, you know what? I'm gonna chime in and just say hi. It's been a while, and we'll have to get in touch again and catch up.
Yeah, sure. Well, you know that since I moved, I got a different phone, but I don't want to give it out over the air. So get a hold of Aaron, and I'm sure he'll connect us up. Okay?
Sounds good. Sounds good, Jim. And like I said, keep up the good work, my friend.
I'll do my best, pal. You take care too.
All right. Thank you.
You bet. Take care.
Okay, let's see. We're on an hour 37 minutes now. If there's no more questions, we can probably go ahead and wrap up here in a minute. If you do have a question, hit 5*, and that'll let me know to unmute you so you can ask your question. Again, coming up in, first I just want to mention, again, if you're interested in Jim's presentations, you can get a 50% discount by using the coupon code JIM50, all capitals. When you go to any of the presentation shopping carts, this little coupon code area, you can enter JIM50, all capitals, and hit the apply button, and you can get a discount that way. Also, again, the conference, the 2020 Energy Science Technology Conference, that's going to be in July 8th through the 12th in Hayden, Idaho, which is about an hour from the Spokane, Washington airport. And we'll have 18 presenters, 20 presentations, 3 panel discussions, and 3 workshops, along with a whole bunch of demos throughout about half of the presentations. Jim will be there. He's not going to be presenting, but if you ever wanted a chance to meet Jim Murray in person, that's your opportunity. Let's see, we have a question. If your number is ending in 9053, go ahead and introduce yourself and ask your question.
Hi, my name is Harold Neslin. I'm from Bellevue, Washington. Thanks for taking the time today, Jim, Aaron. Really appreciate it. I'm going to keep it pretty simple because I don't have the formal education that you guys have. I was wondering if there's any books that you might recommend. I have a couple from Eric and as well as Eric's suggestions that I'm burning through right now. But if there's any books in particular that you might recommend to help me open my frame of reference, as well as if you knew anybody who is seeking a mentee in the Seattle area.
I'm sorry, what was the last thing you said? If anybody is doing what?
If anybody was seeking someone to help with anything going on in Seattle, I have a lot of time at my current state in life that I have that I can donate. I'm not looking for employment necessarily because I don't have the same level of expertise, I'm sure. But if anybody would be able to provide mentorship.
Oh, I see what you mean. Okay. Well, to answer the first part of your question, you didn't really specify what your interests lie in, but if they're electrical and they have to do with high voltage and communications and things of that sort, there's nobody that I can recommend better than Eric Dollard. If you watch his videos and read his books, it's very, very humbling and very, very enlightening at the same time. He has put many, many years into this type of study and activity. And in my opinion, he's one of the best authorities in the world on the subject. If you want to go in a slightly different direction, let me know and I'll try to acquaint you with different books. But I mean, basically speaking, some of this stuff is pretty difficult to grasp without having a firm understanding of at least rudimentary calculus and things of that sort. So you can at least bone up on, pre-calculus and college calculus and things of that sort, so that when you study the physics involved, which makes use and really leans heavily on the calculus, you won't be lost. You know what I mean? If you just want general stimulation, one of the finest books I've ever read centers on the life of Nikola Tesla. It's called Prodigal Genius by John O'Neill.
Oh, awesome. And, yeah, I just found that on Archive. Cool.
Yeah, if you read that, that'll definitely light a fire under you. If you've got the same kind of flame inside as I do. That was one of my favorite books over the years. And there's a lot of stuff by Tesla, or at least about him, which is very enlightening. You have to kind of learn to read between the lines, though, because the poor guy got screwed so many times that he's not always open and above board with the things that he's trying to say. But when you get past that, it's really great stuff.
Absolutely. I really appreciate your time, Jim. I actually have 3 of Eric's books. I burned through the Lone Pine writings, and it was very, very educational and also mind-opening. I'm a little bit out of the state of mind for the vector analysis, or vector algebra. I burned through the first one twice. I suppose that does clarify that question. Would you happen to know, I know that Aaron mentioned I could go online and see if anybody in the Spokane area needed help on the website, but would you happen to know anybody in the Seattle area?
Do I have anything in the Seattle area? What do you mean?
Oh, as far as someone that possibly would need an extra hand, maybe a couple hours a week that I could study under and also help.
Well, I'm a long, long ways from Seattle.
Okay.
So I don't know how to answer that right now. But what you
That's
could
all right,
do
no
is
problem.
write me a letter that has some more specific ideas in it, and Aaron will forward it to me. How's that?
Sweet. Awesome. Thank you very much for your time today. And thank you, Aaron, for putting this on.
No problem. I
Sure.
wish you well.
Hey, and Harold,
Yep. Have a good weekend. Yep.
You're on my one of my Facebook friends, and so I don't know if you can search by location, but if you go through search in my friends list, maybe type in Seattle or Bellevue or something, it might pull up, people who are in that area. Then you could just private message them. A good handful of people who are on my list, are pretty savvy with this kind of stuff. And I do have one recommendation. I've been into this stuff for, a little over 20 years.
Mm-hmm.
And if I could do it all over again from scratch, probably one of the first things I would do is get my basic technician's ham radio license. And it would greatly shorten it would have shortened my learning curve. I still haven't done it. I know that I could easily pass the test. It's about 40 questions out of a pool of several hundred. But if I would have done that 20 years ago, there's 6-year-old girls who have got their ham radio license, so we don't have any excuse. And it's basically a basic electronics course, along with some of the rules and that kind of stuff. But I'd say go to Amazon and get one of the study manuals. I think it's by the AARL, Amateur American Radio, or Amateur Radio Relay League, ARRL, I think that's it. And get the one for the current year. They're usually good for about maybe 2.5, 3 years or something. And get the current one, and if you want to burn through a book, burn through that one, and then you can find a local ARRL group in your area to do the test. But that's what I would probably recommend almost everybody to just do right off the bat. That would have answered so many questions for me over the years. Because besides the basic electrical stuff, then you start looking at a lot of the high voltage, high frequency stuff with what Eric teaches a lot about. And anyway, that would have made life easier for me. So.
Well, I really appreciate it. Thank you for the advice, and I will be looking forward to doing that here very soon, probably at the end of this quarter.
Okay, sounds good.
Okay, thanks again for your questions.
Yep, thank you guys for your time. Have a good weekend.
Yeah, you too. Thanks, Harold. Okay, let's see. We'll do maybe one more question, and then we'll go ahead and wrap it up. And if you could make it brief, Zach, I'm going to go ahead and unmute you. Go ahead and ask your question.
Hello.
Yeah, go ahead, Zach.
What's up? Sorry, I just if you guys have a little bit more time, I'd like to ask another question.
Yeah, go for it.
Jim, I was wondering if you've ever considered using a cone rather than a cylinder for your the shape of your rotor on the Dynaflux.
Actually, I have experimented with almost every solid of rotation that you can think of, and the results are very, very different because they all have different properties. The cone thing I actually did was one of the first things even before Dynaflux, and that was more along the lines of that fellow that we talked about earlier. I can't think of his name right now.
Russell?
Walter
what is
Russell.
it?
Walter Russell.
Yeah, Walter Russell, because he talked about that a lot. And I was fascinated by the Utron design, which was something pursued by both Carini and Getz and a few other people that are all passed on since. That was way back in the 50s and 60s. And I learned a lot of interesting things about that from the geometric point of view. But the ones that made the most sense to me from an intuitive point of view were the ones that I put at the top of my list. I'm sure I could go back and, resurrect 100,000 different ideas that never took off and give them a great deal of attention. The biggest problem is I don't know how long I'm going to be allowed to live, so I'm trying to finish up on the things that I know work.
Yeah. I mean, like, when you do when the Dynaflux starts running, you've talked about, like, a lag in the, so the back EMF is, at least what it seems to me like, is it like it's a spring, kind of. I'm not like an electrical person, but when I listened to your lecture, it sounded like that the peak of the spring, or the pushback force, which is what pushes your rotor back in the opposite direction, how you reabsorb that energy and get it back, seems to be at some point past what would be the crest of the sine wave. So I'm wondering if that's at the crest of the sine wave that the back EMF has its most force, or if it's at the 0 point, right at the what would be the x-axis if you were, looking at it in like a math graph.
Let me put it to you this way, Zach. Trying to describe on the phone what the thing is doing in free space is a little bit difficult, even for me. However, I think I can paint a picture for you that will answer the question roundaboutly. If you consider an ordinary generator of the garden variety type that they sell, in all of these construction sites and places like that to run power tools and things of that sort, if you were to really investigate how that thing operates, there's a lot of little things that you have to know which are generally not taught. And I say that because I'm sure that there's been books about this stuff somewhere, although nowadays if you try to find any information about single-phase alternators, it's like trying to find a needle in a haystack. They go directly from DC machines to three-phase machines, and they skip over that subject entirely. I don't know why that is, but it's very annoying. At any rate, to answer your question, I'll try and do it this way. You know that there's an inductance factor involved in the production of voltage when you have a spinning rotor in a magnetic field within the alternator or within the generator itself. Let's assume that the external load is only a resistor, and not a wire-wound resistor, but a pure carbon resistor, and there's a reason for that. So I don't know the numbers, and it doesn't really matter what they are. But let's assume that you have something like 0.01 millihenries in your inductance, and on the outside of the machine you have a 5 ohm resistor. Okay, so you're spinning the machine, you hook the generator up to the resistor, and it gets hot, and you measure across the leads of the resistor, and you measure the voltage across the component and the current through the component. And I don't care what kind of instruments you have, the best you're going to get is a unity power factor, because that's all there is. Now, let's assume you shut the machine down, you take it apart, you take the rotor out of the thing, put it on a bench somewhere, you take the same load resistor that you were just using, and you attach it with clips or something to the inductor that was previously inside the rotor, and then you power the thing up with 110 volts from a socket somewhere, and you adjust it with a rheostat or whatever so that the applied voltage is the same as the terminal voltage that the generator was putting out. So now, if I go around and do a Kirchhoff analysis of that circuit loop, I'm going to see that I have a voltage drop across the resistor, I got another voltage drop across the inductor, and I got a voltage drop across the source. And those things can be analyzed either with vectors or with differential equations, if you want to get into it, you know, in a really steep way. But the important thing is that you're going to see that there's a phase angle between the current and the voltage across the resistor, and so anyway, if you go around and make all the measurements, you'll find out that there's a phase angle, an electrical angle between the voltage across the inductor and the voltage across the resistor. I presume you know that, right? So let's just...
I'm totally not an electrical person, so I'm trying my best to understand, but I'm more of a mechanical person. I mean, like, so that's why I called in, because the electrical things seem very similar to the other things that I've seen from people that are similar to the person that's like Carini in your life. So you can, I mean, like, I'm sure it's productive to the audience, to, you know, the people that are listening, to talk about the electrical things. So go ahead. But
well, I might as well finish the analogy, because you might get something out of it anyway. So anyway, there's this phase angle there, right? And yet when you reassemble the generator and examine it the way it is when it's running, you can't detect any phase angle. So in one instance, let's say you have a power factor of 45 degrees, a power factor angle of 45 degrees. In the other instance, you have unity power factor. Yet it's the same machine. One way it's disassembled, the other way it's running. So the whole purpose of me giving you this example was to try and instill upon you the realization that when the generator is spinning, there are things happening in the reference frame of the rotor that are not happening when the rotor is out of the machine sitting on the bench. And so they present two entirely different situations. And the reason I brought that up is because the angle that is created between the time that the rotor is under one of the main poles versus the time that it is furthest away from that pole is known as a space angle. And that space angle is a very critical thing to understand. And it's not only important in Dynaflux, it's equally important if you really want to understand a normal generator and how it works. Because it has everything to do with how the energy manifests in both reference frames. For instance, you've heard the term imaginary power, perhaps, because I do have that in mechanics as well.
Like in terms of magnets and things like that?
No, in terms of the in-depth analysis of mechanical systems, there is actually an imaginary component that you can deal with. But what I was going to say was that imaginary power is often confused with imaginary numbers, simply because they have decided to use those numbers to do the calculations associated with so-called imaginary power. But in reality, imaginary power is also real. It's just that it's happening at a different time from what we define as real power. And so in all of these systems, you have to be cognizant of what's taking place in more than one reference frame. And that was the message I was trying to give to you without necessarily drowning you in superfluous information concerning the geometry of the Dynaflux. It isn't only that machine, it's many, many machines that make use of that difference between reference frames. I hope that helps you a little.
A little bit. I mean, is it kind of how physicists describe springs, like in terms of that they generate no power, but if you're to make you can make a system that compresses springs if you take the central axis of something and push it off to the side, so that the spring is constantly compressed, kind of like a rotary engine, and I mean, that energy will transfer. I mean, I'd have to show you. I can't really do it over the phone, but I mean, you can have a system that will transfer the energy through springs and things like that, that you can compress millions of springs over and over again, and it literally requires no energy. And that's the same type of setup that I saw from the person that I've talked about to you before, that's similar to, the Carini in your life. It's essentially a spring setup. If you think about a radial array of springs that are pushing against a central drive shaft, and then you offset that drive shaft from
like
the center. Like a what?
Like a cam arrangement.
Yeah, a little bit, yeah. And it's most similar. I would have to show you with a picture, but
well, we can explore that. We can explore that, when you feel up to it. Just get a hold of me, and I'll give you the time.
Okay. Aaron, are you there?
Yeah.
Is your email address Jim Murray or info@eMediaPress?
Yeah.
Okay, thanks.
Any of the notices, just hit reply. That comes to me. Any of the notices that went out. Yeah.
Yeah. Well, thanks for your time, Jim. I don't want to drag things out. We can do this later.
Okay. Well, good luck to you, and thanks for calling in.
Okay, thanks, Zach.
Yeah.
Okay, somebody else has their hand raised. I guess we can do one last one as long as it's fast.
Well, it better be, because my phone is about ready to quit anyway.
Oh, okay.
But we'll go as long as I can with this particular call. How's that?
Okay, so let's see. I'm going to unmute somebody right now. If you can keep your question, to 10, 15 seconds, and then we're just going to have to wrap it up. So go ahead and introduce yourself and ask your question.
Hello. Thanks, Aaron, and thanks, Jim, for making this call available to us. My question is,
what's
Jim,
your name?
Hello?
Yeah, what's your name?
Oh, Frank, California.
Okay, thanks, Frank.
Yes, thank you both for making this call available. Jim, during this phone call, when discussing your work, you've mentioned varying inductance. Does your Dynaflux alternator or the transforming generator, does it involve a parametric operation?
Oh, the Dynaflux definitely does. The transforming generator can be induced to do so, but in certain modes of operation, it does not exhibit that characteristic. I am quite familiar with the use of parametric arrangements, and several devices that I'm working on do use that approach. But the Dynaflux definitely does. I mean, everything about it is parametric. As a matter of fact, there's so many things happening at the same time that it's taken me years to understand what the damn thing is doing.
Okay, I'm very interested in that. And so, which presentations mostly do you discuss that parametric operation, say in the Dynaflux Alternator presentation or your transforming generator presentation?
Do you know something? I'll be very honest with you. When I make these presentations, just like this one, I speak ad lib. I speak extemporaneously. The question cues the information, from my subconscious and from my memory. But an hour later, I don't remember half of the stuff I said. So
I get where you're coming from. I think I'll go ahead and get both of those. I'm interested in more details of your work.
Well, I was going to suggest that you ask Aaron. He's probably more familiar with them than I am because he created them. But I think that I get into some of that in the Dynaflux presentation. Believe it or not, I may even touch on some of that parametric stuff in the very first presentation, the Tesla Hidden Secrets or whatever it's called, because the whole thing that I did in Michigan was very parametric in nature. I mean, if you understand how a synchronous capacitor works, there's a lot of parametric relationships going on right there, and that was the basis of the first experiment, which gave birth to the Dynaflux device. So I'll leave that up to you to find out which would be the best thing for you to study, if it's okay with you.
Sure. That sounds good. Yeah, thanks for that information. And with that, I appreciate that discount code you're making available too. So I think I'll just go for the presentations you have available there. And one last quick question. I know you're trying to wrap up. On when you brought up the early experiment with a power company where you had to use that 2-to-1 frequency ratio, did that involve a standing wave?
Well, I don't know the answer to that for sure because I wasn't monitoring the transmission lines, but more than likely it did. And the reason I say that is because the voltage and the current built to the point where if there was no standing wave, there was certainly some kind of resonance involved. But, when the line blew, it ended the experiment. So I wasn't about to repeat it, considering what happened. But I have seen similar situations in Tesla windings, in Tesla-type windings, where there's definitely standing waves. See, I always believed that regardless of what the radio community was trying to achieve with early Tesla windings, to just wind a Tesla coil so you can have these great big sparks is not necessarily, unless that's what you're after, it's not necessarily a practical achievement. So when I was studying one-wire communications a bunch of years ago, or one-wire transmissions in general, the first thing I did was I applied the right value of capacitance to the inductors involved so that there was no sparks. And when I did that, it maximized the current in the ground loop. And measurements were a little bit tricky because of the high voltages and stuff like that, but what I recall from the images I saw on the scope was that we definitely had standing waves or double-sided waves, or whatever you want to call them, that were involved in that. And so,
yeah, I'm very interested in that also. Do you discuss that in any of your presentations?
No, I don't consider myself the real authority on that, but I know darn well that if you're interested in that sort of thing, there's another gentleman associated with this group that could certainly help you. Maybe you want to write a letter to Eric Dollard and ask him what you could study that would acquaint you better with his work in that regard, because he's the real master when it comes to that stuff.
Yes, okay. I'm very familiar with his work, and I have studied his work, and I've called in on his calls. I just was curious if you had and was interested in anything you might have presented.
Well, I'm interested in it, but I can only do so many things, so I kind of have that at a lower priority on my list.
Okay. Well, thank you very much, and I know you're working on wrapping up the call. Thank you very much, Jim and Aaron.
Okay.
Okay. Well, it was a pleasure talking to you, and I hope some of my stuff helped you.
Yes, it did. Thank you very much.
You're welcome.
Okay. Hey, since I have you and Eric on the same call, I just wanted to kind of get some clarification on something real quick. This concept of like the, I guess I'd call it parameter variation, or this parametric business as it relates to these rotating capacitors. I talked to you about it, and Eric is working on some stuff where I might be able to show a demo at the conference. Eric, are you there, or can you hear me okay?
Yeah, I'm here.
So you mentioned that you had some Russian paper or book or something relating to this, and not that long ago, Jim, you kind of described to me that there was a Russian paper or a book that you had a copy of, but you didn't know where it was. If you're able to describe that, I'm just trying to see if the paper or book Eric has is the one that you were describing, because I'm trying to get this information together, and if he already has it, I don't want to keep looking.
Well, I got that. I think I know where that paper is at. Now that you reminded me, I'll dig it out and get it to you.
Okay.
Okay, is that enough for you, Aaron, or do you want me to try and regurgitate what I remember?
Yeah, if you can kind of explain a little bit about it, and then once Eric digs it out, we can see if that's actually the one you were talking about.
Okay, well, the one that I remember was, I'm pretty sure it was published by University of Moscow. I don't know who translated it, but I got a hold of it while I was in Michigan, and I read through it and played around with some of the ideas in there. But basically what they were doing, they were building RLC circuits that did not have an external source of excitation. In other words, they didn't have an applied voltage. But what they did do instead was they varied the capacity mechanically, or they varied the inductance mechanically, and without making reference to any external voltage, it brought up a resonant current in the system. And then they were studying the relationship between the torques that it required to produce this effect on the mechanical shafts and the overall work that was being done in the circuit itself. And of course the math was pretty horrendous, but nonetheless, they were looking for like a sweet spot, for lack of a better word, where they could get away with a minimum amount of shaft excitation for the maximum amount of electrical work done. And as I recall, there were something like 50 pages maybe in this report, and copious diagrams and calculations. I know I have it because I would never part with something like that. But unfortunately, I've moved to so many places. It's most probably in New Jersey, although I really can't tell you exactly where it is. But if I come across it, I'll be happy to share it with you.
Okay, great. Okay. Well, I guess we can go ahead and wrap it up. I really appreciate your time and everything that you shared on the call. And again, if anybody wants to come to the conference, it's EnergyScienceConference.com. And 1/3 of the seats are already sold out, and with about 4 months or 4.5 months left, all the seats sell out every year. It's going to be a jam-packed event with a lot of demonstrations. You can find all of Jim Murray's presentations on emediapress.com. If you scroll down on the homepage of emediapress.com, you'll see the 2018, 2019 presentations. But if you mouse over the home, H-O-M-E, the home link in the main menu bar, you'll see something pop up that says Home 2, and that's the old homepage where you can scroll down and look through it. All the other, that's where all the Jim's presentations will be. And I'm working with somebody right now that we're going to rebuild the whole catalog and everything, so I know that website is horrible, but in any case, I guess that's about it. So I'll do my best to get this on YouTube in the next week or so. And any final comments or final thoughts, Jim?
No, not really. I think I did my best to be as open as possible and succinct, but I am looking forward to being contacted by the guys that expressed an interest in further talk with me, and I hope that they follow through. Other than that, I appreciate your time, and as always, it's wonderful to interact with you guys. I look forward to seeing you this summer.
Okay, same here, and thanks for being on the call, Jim, and thanks for everybody for calling in. Have a good weekend.
All right, you
Have a
too.
good weekend.
Bye-bye.
Okay, thanks, everybody.
Thanks again, Aaron and Jim.
Yep, thank you, Aaron.
Thanks, everybody.
Jim.
Thank you. Thank you.
Bye-bye.